Okay, ladies and gentlemen, I want to talk to you about a few things. One is equilibrium, as I like using it, not the engineering term, but this engineering term, equilibrium.
Equilibrium.
I state this equilibrium,
Equilibrium.
a state in which opposing forces of influence are balanced. Let's jump right into tide arch bridge, which I like to refer to as a tide back bridge, tide back. You can Google this and come up with different products, but different versions of this. But this will help you. Imagine a load pushing down on this and this on this shape here. All right. So as you push down on this shape, and these weren't connected, what would happen to the two ends here? They would push outwards. Now imagine if I was down here and these weren't these. Imagine I could pull down on this and these weren't connected right here. No connection and no connection. This was still here lying on top of here, but no connections besides right here. As I pull down on the center of the structure, this would still have the effect of pushing the ends out, correct? Remember, they're not connected there. So you see what happens when the load it just wants to naturally push out on the ends. So what do? Well, you tie it back. You can make a connection into the steel here, making a tied arch system. So as it tries to push out, since it's connected here in steel, it has to try to push the steel here out. It puts a huge amount of some compression and a lot of tension in this steel member, trying to push it out as it's connected. Now watch where I go with this. So we come over here to this structure here. This is the FIU bridge. We'll only use this structure here, please. This section here, which we know that collapsed. Now the same thing applies. Naturally, the dead loads, the unsupported spans. That means here's a support here and a support here. The column here. This is the river over the where the fail then is down here. As the unsupported spans, just by default, everything it will want to deflect down in the center. How do they stop the deflection? Well, Denny Pate states that he has a redundant system, that the deck alone, and I said this in one of my very first videos, and a few engineers called me quite a few names, and I actually had to block that video because they were just beating me up because they had no belief in my statement there, and I got called everything in the world. But it turns out it's exactly what Denny Pate made, a compressive system, and that these were not designed to be in a truss design system. So what we have here again, let's go back to this, is that the deck, would imagine it as that it's just concrete, but they added the steel. The post tensioning is able to make it. You make it so tight. You compress the steel in here that you're actually elongating the steel so tense. A rubber band. Pull a rubber band. Hold the rubber band in each one of your hands. It's very loose as you push in the middle. Now, if you pull a rubber band tighter and now put that same weight on there, it's not going to be able to push down, is it? And you pull it even tighter and tighter, you're going to be able to add more and more weight to it. Well, that's the way these steel cables work, if you will. They pull them tighter and tighter and tighter to the point where this deck alone can't push down. It can hold its own weight, the concrete dead load. And then they add so much more steel in there, those post-tensioning in the back of it, across the back end of it, as we know in other images I show you. The post-tensioning, those caps, those black caps you guys see, that makes this whole deck so flat and tight that it won't deflect. Theoretically, it will not deflect. And then Denny Pate made the canopy. It's smaller than the deck below. I think it's 16 foot wide. The deck below is about 32 wide. And this is a canopy, a decorative detail that will keep the rain off. Decorative detail. It's not supposed to be structural. That's not part of Denny Pate's structural detail. He then reinforces it with supposedly not structural. He then reinforces it with theoretically not structural, because you have the deck here. Theoretically, I should be able to take this all apart and lay it on the deck. It's just a dead load to Denny Pate's design, because the deck alone, he said it can hold it. And then we have these post-tensioning truss members, which Denny Pate now claims is a redundant system. But they're all supposed to be in compression as per the interview, as you heard Linda Fig and them said. It's all a compressive system. So it's not acting if it's all compressive, then it needs this to work too. It's not acting as a truss system, as a system that you push down on one, it pushes up on another, pushes down. It's not acting as that. And this can't act as that either, because this can't go in tension and all that. I don't want to confuse you with that. I'm just saying he double dipped. But let's go. with that said, his deck alone is 100% in compression, and it should not deflect. It deflected, and per the engineer asking, hey, why is it some deflection? The engineer did not say we have cracks because of deflection. The engineer that the BPA just asked, why is the deck deflecting? And the engineer said, don't worry about it, that's okay. That's okay. It's post-tensioning. This is not rebar in here that has to become active. You get a little deflection and the rebar becomes active. This is post-tensioning. It's active from the start. So any deflection in this deck and you have post-tensioning in it, you now are your post-tensioning is showing it's getting even more loaded by the dead loads. It's not. So when they removed the scaffolding, it deflected down. By doing so, it acted like a tied arch bridge at that point. So if this deflects down any amount, I state any amount, because this is flat. He has no design here that shows a curvature in it. This is shown as plumb and flat. This is shown as level and flat. It's actually at a plumb over here design. So and there's a slope for handicap reasons and water runoff, but handicap reasons. The maximum slope. So this I state can have no deflection in it. Any deflection down, look what happens if you deflect. These two are interacting together. If you deflect this down, what happens? You get a moment. This is going to push out there. It's going to push out here at 12, and it's going to push out here at 12, and here's number 1 and 2, and it's going to push out at 1 and 2. As you can see in this design, number 1. This is the 2016 rendering. Number 1 and number 2 are not interconnected. Look at that huge gap, as this is a scale diagram. Look at that huge walkway in here. You could walk through that. Over here on number 1 and 2, they're interactive, but a little bit of a walkway. He had it initially going down to the deck. Then all of a sudden, now we have a detailed change in 2017. And I wish I could find those 2016 plans. I'd be able to really show you guys some stuff here. Now all of a sudden the chamfers have been added, and this is the detail. 16 foot I called it, and 32, whatever, 31.8. So now we have the loading. Let's go over here now. Now he's interactive. Now it's actually touching. 2016. So you can see the renderings. What I'm driving is they had multiple people doing the rendering and computer modeling of this. Now all of a sudden it's touching exactly, and we're over here. But again, let me give you the teaser again. So if this pushes down by default, this column, if this sags down, this has no choice but to want to create a crown in here, a bow in here also, and a bow down here. And this wants to push out there. It creates the stresses here in the nodal areas, obviously. No choice by default everywhere. So the stresses are really taken up here. They're really taking up on every connection here. And down here too. But now we have this little bit of 11 and 12. So as it pushes down, and I'm going to do a model of this, guys. I'm going to make one up. I just haven't figured out how to do it yet, of styrofoam or spray foam. I'm going to work this out to show you how this pushes and how that deflection results in exactly this. Let's go to so on this one, you go to FIU bridge collapse, NTSB report debunked, cracks appear 2 days or move before 2 days before. 2 days or more before bridge move, part 2 of 4. Here is 46. So if you click on these things right here, it should pop us into 46 right there. 46 shows you, let me pause it, that on 2/8, this is 2 days, they didn't even have the transporters underneath of this thing yet. And this crack right here is presented. This is that sagging, and that's because number 11 is pushing, number 11 and 12 are interacting together. Remember I said it's pushing together? It has no choice in this design to push outwards. In this concrete interactive design, we see because he added a tie back, and see these are just hangers, right? But because of the bridge design having post-tensioning bars back to this nodal area here, number 9 and 10, and back to the base of 11 and 12. And bear with me, I'm going to pause this. You don't have to bear with me at all. So here's the point I'm making right here, is that this is just a tie-back arch system. And here's your tieback as it loads, since we have deflection stated by an engineer, stating that the more than one engineer, because one questioned it, the other one agreed to it, stating that it's no big deal, no big deal. But yet that big deal of the cracks, he did not tie the two together. The one engineer at the BPA recognized the sagging. The other engineer said, it's okay. And neither one of them tied it to the one most important crack right here. This crack was when obviously the sagging that took place before they put the transporters on it, and after they removed the scaffolding. After they remove the scaffolding, this appears. But they don't tie it together. They don't put it together. That this crack, watch when I click the next scene, it's going to be exactly this crack, the same one. That's that crack. It's now developed to this. After they detension. So after they detension, after they release the tieback, remember a tieback arch system, how it connects right here? Well, I state that number 11 and number 2 had the intent of being a tieback system, that it was holding this bridge together, number 11 and 2. Once they detensioned it, it went into the air. Now, let's go back to this one. See the importance of this? It went into the air, upwards into the air, meaning it lifted up, not down. This is an upwards lift. We go back to 46. You can, if you dive into this deeply into the photograph, I mean not the video, you'll also see that this is already presenting an upwards, not a pushing out and falling down. So not just that slide action thing they're talking about. My definition, and will explain all the tension cracks, why they're all open, not compressive. They're all open cracks, because when you look at it, and I always said this was sagging, the bridge was sagging, and I only had one image, if you guys remembered. I did not have this one. I had the image of the chamfer saying, wait, this is indicating the deck is sagging. And then I kept arguing what came first, the deck or the canopy. You guys remember that? The deck or the canopy, and I called it the chicken or the egg. Which one came first as far as the cracking and all that? Now that we have all the evidence, all this evidence, rather, we don't have it all. This elevated. So how did this elevate? Because it's still connected here. They detensioned it, but it's still connected here in number 10. And as it sags down, number 10 has, and this is all connected in the canopy. All this is interactive, connected. It's sagging down. The clamp force is lost in number 11B, and this will be 11A. It's lost. It allows it to lift up into the air like that. And then it came to a stop. Why did it come to a stop and not go to the ground? Because they only loosened detention number 11, and then it popped cracked like hell. The crack like hell was already present. Crack like hell was already here. This is the same thing as crack like hell. All it did was open up. It didn't crack like hell. It expanded on what it already had. That's all it did. It just raised up in the air. When he took off the clamp force of the back of number 12, it killed the tied arch system back to here. And it's as simple as that, is that this system was acting like a tied arch system. They missed it with the deflection and not tying in every single crack. And this is why I say I'm a crack freak, right? And why cracks matter. They are signaling everything. Those little bit of cracks are telling you what your structure is doing. You shouldn't have any cracks in your structure, in a concrete structure that you can't exactly call ahead of time. So if it's going to sag in your spans and you had developed a crack, you need to identify why to develop the cracks there, and then what's the weakness after you created the crack. What's going to be the weakness? And if you're so bright, you'd have already said the crack. I predict a 1/4 inch crack, and at this point we will now go at this crack and we'll use sealing the Baccarat and Sikaflex or whatever. Or this is not logical to state that cracks are okay. Now I know in engineering everybody says not a matter of when your structure is going to crack, but it's not if, but when. I think that's terrible. It's terrible. Concrete is a great product as far as telling you where your stresses are, though, because they'll identify themselves as cracks. Steel is not going to be that easy to identify itself. It wants to, hide the forces internally in the steel until you finally get something to show, like a buckling, a torsion, a shearing action. It's not going to be that easy to identify itself. Of course, it identifies itself if you can see the deflection. It's up to you now to extrapolate what the deflections are doing on each joint. And this is all we're looking at now. The sagging is not just a freebie. In an interlock system like this, you can't have sagging. You're going to have shear moments and things like that. If you have sagging, this sags down. The concrete here will now start acting like a load on all these bars. It would act like a lateral load on the bars. Or how much did you calculate that shear reaction on the bars? And now the tube, the plastic ductwork, will now be engrossed into it. And that's why if you had concrete, you grouted these closed, now it's going to act as one. But it's still going to be shear. If it's all concrete grouted, and the shear reaction is still going to be there, it's going to be up top here and down here. Remember, this is not it's got some reinforcement, but it's not really that's not its intent. It's a stirrup connecting. So when they released it down on this end, they had cracking also. This had a big force, everything going on. Cracks appeared in this one. Same thing. Those cracks in that arch. I mean, in this design down here, in this Fresnick, whatever the guy's name, the inventor of it. He's those cracks also were tension cracks. The same thing that went down here, went down here. Went down here also. Remember, this is lifting, not being pushed off, lifting. I will delete every single one of my videos if someone can tell me that this is not lifting off. NTSB, they're inept. Those engineers, they're inept also. Any engineer who says it's pushed off, it doesn't recognize this as being related to, let me put it this way. Any engineer doesn't recognize these two as being related, I find them lacking, period. I don't care if you got 17,000 PhDs. If you can't see these two are related, then I don't find you lacking. You have what I call your amygdala is protecting you because you made a conclusive file that says, oh my gosh, I can't believe him because if I believe him, that means I was wrong. And I can't be wrong. I can't be wrong because my ego won't allow it. And so your brain, your amygdala will protect you and say, no, he's a crackpot. He's this. It's him. So your ego will then tell you your amygdala will tell you attack the source, meaning attack me. Because you can't have this exist because your ego says I was wrong. It's very hard to tell yourself you were wrong unless you teach yourself that, like I'd put on my channel, I will make mistakes. And when I make them, I will correct them. That's how you're able to tell yourself you're wrong. Sometimes I run across something where it takes me a minute to go, darn it, and I grit my teeth. I know I'm going to admit to being wrong, but I'm like, oh, I was so invested in that. And then I go, nope, I was wrong. So now with the new data, again, if we have more, this is elevated. This is elevated. This right of the screen here, left of the screen here, north or south, however you look at it, is showing its exact location. There's the pipe here. We know that this PVC pipe, and they're interactive. It's the same friggin' crack. It's elevated already. This is just a tied back arch system that they made, and it was identified immediately with the deflection because there should be no post-tensioning deflection in this structure on the span. What created it? That's another thing altogether. It's all about maybe center loading, maybe created this overloading, or not being able to get it over to all of the post-tensioning all over equally across the deck. I always said it was a problem putting it down the middle, but let's don't get focused on that. Let's more talk about the sagging. The sagging, again, caused the tied arch, this sagging of the deck, caused a reaction of this pushing down from here. So the hinge point would have been from here, this point here, so number 3, and number 10, more the hinge point of creating this new triangle that lifted up. after they detensioned. After they detensioned this allowed this just to dip down even further and to crack like hell. As I told you, if they would have ran a new line across there, they would have seen a significant amount more sagging. But Denny Pate and all those engineers, including FIU, I just find it just really, I'm so disgusted with most engineers, just so you guys don't know that. I really am. I really am disgusted because for most engineers don't see the simplicity of forces, that they're stuck too much in the math. And this just makes them academic engineers. You know, you're losing the ability to evaluate. If you don't have the ability to evaluate, how are you an engineer? So I guess I'm attacking engineers now. But, you know, I attack everybody. So the firemen that were on my video said, I attacked the firemen. It's all fair game, baby. I attack myself too. So I'm fair game. I've debunked my own video saying debunking well, in the last one I said I debunked that. First I said it appears that the transfer slab might have failed in the NOLA thing. That would cause a reaction down there, dropping the structure downwards. And then sat on it for a couple of hours, and I said, nope, debunking myself. And I did a video saying debunking myself. And I put it out there. So no, but this is this. If anybody can tell me that that's not elevating and prove it to me, I'll delete every last one of my videos on this FIU structure and put up one video saying how awesome you are and how you enlightened me and how I was wrong. Also, we'll give you $1,000. So you can consider this a bet. Not a bet. That's illegal. You can consider this my bounty for you educating me, my educational bounty towards you, towards a fund, a charity, whatever you like, whatever way we would keep it legal to transfer $1,000 from my possession to whatever way we can. I will delete all the videos as you instruct. They shouldn't be up there if that's the case. And $1,000. If anybody can show me that this is not this crack and those aren't the same and they're elevating the elevation of this. Look at this. Look at that turn there, that profile, that shape. Look at that turn there. See that little profile and shape? I mean, they're just like awesome together. They're awesome together. That's it. Anybody can tell me that this is not raising up in the air, the back end of this is not raising up in the air, and my explanation doesn't work for raising it up in the air, you got the grand. You got the grand. Now, only one exception to that, if somebody put hydraulics under here and lifted up after they said crack like hell, and we're looking at a hydraulically lift, the wild card, that somebody went out there and put a hydraulic jack under there and lifted up. Come on. That didn't happen, but, you know, I've got to name the wild card craziness. They put shims under there. I will not count the shims against this. They didn't put the shims didn't elevate this. They didn't jack it up to put shims there. So I'm not going to count. So you can show me the shims, and I will not count those as them having to lift this up. It's not possible with those shims and that equipment. Just not possible. So I won't hold that against you. Again, that's an elevation change. This is simply a tied arch bridge system that Denny Pate created by accident because that wasn't his intent. When he released the end connections here on each end, this allowed the bridge to sag further. Of course, being tied in with the truss members the way they are, it was able to pull down, pull up, pull down, pull up. It went down. This sagged down. Consequently, this interaction of this member here was able to pull, and across the steel here was able to lift this up to just a degree where it re-anchored, where it stopped because the anchor was still in here and this bar was not fully denutted. I like that, denutted. And it re-grabbed, and that's why we see a stop in time again. That's the new equilibrium was established, and that's what I use the term equilibrium on, so you guys can understand. The new equilibrium was established, and that was established at that time. You would then watch the structure over many days, and maybe more cracks would develop as it's still trying to resolve itself, finding equilibrium. The structure right now is in equilibrium, as we look at it in the image. But yet forces are still present as rust develops, etc. New equilibrium is established. Ultimately, the rust can totally weaken this joint. New equilibrium being established all along. This bridge being not being able to take the full loads, and ultimately can't even take its own self-weight under that equilibrium load, and then it collapses on its own, if you let rust go right onto its own failure. That's the same thing that happened here. It's just a tied back arch system that lost its tie back connection. I'm going to terminate the video and load this up. And I welcome, and this is one of my third renderings of this, so I welcome you guys to fight it. And remember, it's $1,000 for somebody who $1,000, for the bounty for my education on this. Anybody, even the ones that hate me to do it. So if I blocked you, your game, you get $1,000 too. Just you got to write me on the side, do a new channel, whatever. Anybody I block, this is up for $1,000. NTSB up for $1,000. I'll give to them because you're allowed to lobby them. I'll give to them through whatever source I can, lobbying, whatever, just say I have nothing to say. Anybody. I mean, anybody, entire world, this is up for. Wherever you are in the entire world. So if you're one of those small countries in Asia, $1,000 US dollars means that much to you. It's a lot of money. It's yours for the taking. Yours for the taking. I'll delete all the videos, send you the $1,000 some way legally. All right, terminating video. Nobody's going to be able to defeat this. Here's the bounty.